Welcome to this explainer. I am so thrilled to have you here today because honestly, we are about to completely shatter your textbook expectations of what a tornado actually is. If you think you know exactly what these storms look like, how they behave, or, where they can strike, definitely prepare to have those assumptions challenged. We're diving into some truly mind-blowing source material that shows tornadoes are far more diverse, deceptive, and dangerous than just a simple spinning funnel. So let's just dive right into this.
Okay, I want you to really think about this for a second. Where is the absolute last place on this entire planet you would ever expect a tornado to form? You're probably picturing somewhere freezing, mountainous, and completely devoid of that warm, thick, muggy air we usually associate with severe weather, right? Well, if you guessed the highest mountain range on the planet, you hit the nail on the head. Researchers have actually documented a tornado forming in the Everest region of the Himalayas, literally at 12,000 feet in freezing, bone-dry air. Now, you might be wondering, how is that even possible? Well, during monsoon season, warm, moisture-laden air from the Indian Ocean gets violently pushed up those southern slopes. As it rapidly rises and cools, it just slams into the frigid mountain air above. And if the wind shear is just exactly right, that collision creates an impossible rotating column in an environment that should, by all accounts, be completely hostile to tornadoes. It entirely breaks our basic meteorological assumptions. Which brings us to Section 1, Beyond the Classic Cone, Shattering the Textbook Illusion. So the textbook expectation is that visible, neat little spinning cone dropping down from the sky. Take the massive Tuscaloosa EF4 back in 2011. It spent much of its 80-mile path looking like a dark triangle, a storm that tragically took 64 lives. But relying solely on that specific visual expectation is incredibly dangerous. The terrifying reality is that tornadoes can be massive churning wedges that cause optical illusions, or completely invisible columns of wind, or even literal threads as thin as a telephone pole. Let's look at how this builds, because a tornado can rapidly escalate its physical shape. It often starts off as an elephant trunk, sort of leaning and curving gracefully as it pulls in moisture, like that really famous, heavily photographed Simla, Colorado tornado in 2015. But as it thickens and yanks in massive amounts of warm air, it stabilizes into that classic cone shape. The absolute most terrifying escalation, though, is the wedge. These are massive, solid walls of churning clouds, sometimes over a mile wide. Entire towns can fit in their path. And here's the really deadly psychological trick. Because they are just so massive, your brain literally can't process their 30 to 50 mile per hour speed. They look like they're just creeping along in slow motion, which tricks people into wasting critical escape time just standing around and watching. The physics of angular momentum brilliantly explain why size does not always equal safety. The conservation of angular momentum basically tells us that as a rotating object's radius decreases, its rotational velocity dramatically increases. This is exactly why rope tornadoes, which actually often happen as a storm is dying out, are deceptively violent. They might only be 50 to 100 feet wide, looking like this graceful, swaying little ribbon, but all that rotational energy is violently compressed. They can easily pack highly focused EF2 or EF3 winds, entirely destroying a structure in under 5 seconds while looking fragile doing it. The crucial takeaway here is that tornadoes are completely fluid, constantly evolving anomalies. Just look at these bizarre variations. Needle tornadoes, like one documented in Copo, Colorado in 2016, are as thin as a telephone pole, completely starved of moisture, yet they're spinning at 80 to 90 miles per hour. Then you've got hourglass tornadoes, like the one in Ray, Colorado. They literally look pinched in the middle because powerful ground and flow and upward lift completely overpower the mid-level air. And finally, the stovepipe, perfectly vertical and uniformly wide. When you see a stovepipe, like the Andover, Kansas EF3 in 2022, it means the storm's completely locked in and operating with brutal, terrifying mechanical efficiency. Moving right along to Section 2, the invisible killers, sensory blind spots. Now I want you to put yourself in this terrifying position. You are staring directly at a storm, and your eyes are completely useless. A rain-wrapped tornado can pack 150 mile per hour EF3 winds, but it's entirely hidden inside thick curtains of gray rain. You get absolutely zero visual trigger until debris starts hitting your house. Or consider the invisible tornado. Remember, a tornado is just a rotating column of air. The funnel we normally see is just condensed water vapor. If the air is too dry, that moisture never condenses. The violent rotation is there, Doppler radar sees it perfectly. But visually, there's nothing, right up until structures start tearing apart. And then there's the absolute terror of the night tornado.
This fragmented visual input is exactly why night tornadoes are disproportionately deadly. During the day, continuous visual input lets your brain accurately process distance, speed, and the overall threat level. But at night, you are plunged into pitch-black darkness, entirely reliant on totally irregular lightning flashes. Your brain is only getting these fragmented snapshots. In one flash, the vortex looks a mile away. In the next fraction of a second, boom, it's 200 yards closer. The human brain just isn't built to process threats this way, causing our ability to judge distance and speed to completely break down.
Let's look at Section 3, Monsters and Anomalies. This is when the rules completely break.
Imagine looking at a tornado and seeing multiple smaller tornadoes aggressively rotating inside of it. These are known as suction vortices. They orbit within the main tornado's broader circulation. Now, they might only appear for 30 seconds before dissipating, but their intense rotation is layered directly on top of the parent tornado. This means you could be in a shelter rated for EF3 winds, which might easily survive the main funnel, only to have a localized suction vortex drop EF5 winds directly on top of your head. It creates this horrific, completely random damage pattern where one house is totally erased and the one right next door is practically untouched.
As if that wasn't chaotic enough, look at these anomalies. Twin tornadoes occur when the atmosphere is so unstable, it basically refuses to consolidate its energy into just one funnel, producing two fully independent violent tornadoes at the exact same time. Back in Pilger, Nebraska in 2014, two EF4 tornadoes, with winds over 200 miles per hour, carved parallel paths just a mile apart. Think about that. If one blocks your escape to the east and the other blocks the west, where do you even go? Then we have satellite tornadoes. These spin up quickly and orbit a larger primary tornado. They are incredibly dangerous because everyone, including the radar, is totally focused on the massive main threat, allowing the satellite funnel to curve in unseen and strike from a completely unexpected direction. And then we have the literal rule breakers. So in the northern hemisphere, every tornado spins counterclockwise. Radar is calibrated for it, spotters are trained for it. But very rarely, along the outer edges of a supercell, an anticyclonic tornado will form, spinning completely clockwise. Visually, from a still image, you can't tell the difference. But when highly trained storm spotters see it in motion, their brains immediately recognize that something is fundamentally wrong. That hesitation, just trying to reconcile backwards motion for all their training, can cost critical, life-saving seconds. This all leads us to a formation so deeply unsettling, veteran storm chasers actually gave it a chilling nickname: the dead man walking. This happens when a main funnel body is flanked by two distinct debris columns, creating the highly sinister silhouette of a giant human figure striding across the landscape. As one storm chaser perfectly described it, "It didn't feel like I was watching a storm anymore. It felt like something was walking across that field with purpose." While there is no scientific proof the shape predicts intensity, it shatters that mental barrier between a mere weather phenomenon and a literal monster that looks like it has deliberate, terrifying intent. Let's wrap up with Section 4, Extreme Environment Tornadoes, Elements of Chaos. 2,000 degrees Fahrenheit, that is the extreme heat required for a massive wildfire to generate powerful, rapidly rising updrafts. When surrounding winds introduce rotation into those updrafts, you get a fire tornado. And to be clear, these aren't just little fire whirls you see in campfires. These are massive tornadic vortices, pulling in pure flame, ash, and burning debris. Let's break down this entire matrix of elemental madness. During the Carr Fire in California, a fire tornado actually reached EF3 intensity, packing 100+ mile-per-hour winds that warped solid metal and destroyed 1,000 structures. You can't even track them on weather radar because there's no precipitation to bounce off of. Then look at volcanoes. During the Kilauea eruption in Hawaii in 2018, rising plumes of superheated gas and rock created literal lava-nados, spinning columns of molten rock and spontaneous lightning bored entirely from volcanic material. What about freezing temperatures? In January 2013 in Ontario, cold air moving over warmer water created a ghostly, translucent snow tornado right in the dead of winter, packing EF1 winds. And finally, coastal waterspouts. People often think they're perfectly safe if the spout is over the ocean, but when a tornadic waterspout crosses onto land, the increased surface friction actually tightens and intensifies the rotation, instantly turning it into a deadly inland threat. And that circles us right back to this number, 12,000 feet. In July 2004, a hiker photographed a tornado at Rockwell Pass in Sequoia National Park. It is the highest confirmed tornado in U.S. history.
The air was incredibly thin, and the funnel was quite faint because moisture struggled to condense, but the mountainous terrain funneled the wind perfectly to create a localized zone of intense rotation. It proved that even high altitude, thin air, cannot always stop a vortex from organizing.
Which brings us to our final provocative thought of the day. If nature's most violent windstorm can adapt to the freezing peaks of the Himalayas, the 2,000-degree inferno of a wildfire, the molten ash of a volcanic eruption, and even the dead of winter, are there any environments on Earth where we are truly immune? It really leaves you in absolute awe of nature's terrifying adaptability, doesn't it? Thank you so much for exploring the extraordinary with me in this explainer today, and always keep questioning what you think you know.